Okay, so we have the pleasure to have Professor Sergey Yakovenko today from Weizmann Institute of Science, Israel, and he's going to talk about Fuchsian equations with a small parameter before the highest derivative. Thank you, Sergey, for accepting and go on, please.
Okay, I'm pleased to give a talk in this audience, and I'm pleased to see so many familiar faces and friends, Pablo, Jessica, well, whomever I could not recognize here. So that's great that Hossein and Eunice could arrange such a conference. I should say that yesterday I was very much impressed by the talks by Paula and Colin, who really explained solution of a very natural, long-standing problem. It takes lots of efforts to expand. So my talk will be, in a sense, an opposite. So the result that I'm going to talk about, the final result, is not new. It is about 10 years old. This is a solution of the infinitesimal Hilbert 16th problem achieved with Gary Benjamini and Dmitry Novikov. But there is a very important ingredient in solution of this problem, which, well, I realize that it deserves to be promoted and advertised because this looks like a powerful tool. And, well, as you know, in a paper 60 pages long, all auxiliary methods are usually buried so that nobody can get them from there. So I will tell you a story about some kind of Fuchsianity, but not with respect to the independent variable. So well, the details will follow, but rather with respect to parameter. So what I'm talking about is the following. So I start with a crash course on linear differential equations. So what we study is a differential operator of the following form. So that's what you study usually in the undergraduate course of differential equations. The difference is that, well, D, of course, stands for the usual derivative of independent variable time, but we assume time to be complex, and we assume that the equation is globally defined. That means that the coefficients of this equation are rational functions of t. So the natural domain of definition is the projective line, with the usual caveat that coefficients may have poles at which where they have infinite value. What is also important is that we study homogeneous differential equations, which means that the differential operator makes sense up to a multiplication by a constant or a function or whatever you want. Using this degree of freedom, you can always assume that actually the coefficients are polynomials in T because you can get rid of the common denominator. And by the same token, you may assume that those polynomials are mutually prime. There is no common factor that can be canceled. And therefore, we're dealing with the algebra of non-commutative algebra of differential operators. So this algebra sometimes is called the Weil algebra because, well, the identity, a non-trivial identity means that the commutator of T and D and the derivation is 1. That's the usual Leibniz rule. Now, this equation has the leading coefficient A0 of t, which we always assume to be not identically 0. Otherwise, we just decrease the order by 1. Now, the roots of these leading coefficients, assuming that the rest are polynomials, are singular points, because near those singular points, you cannot express the highest derivative as a function of the lower order derivative. And eventually there is a singularity at the origin because, well, the fine chart is not very good to deal with the origin. Solutions of those differential equations are multivalued analytic function with the natural domain of definition, which is a complement to singular points. And usually they are ramified at those points. That's the phenomenon that is that will be mentioned many times. And of course, what people did starting from mid-19th century at least, the French, they tried to classify singularities of those differential equations. Those are, well, I listed three types. Actually, there are essentially two. One can have a removable singularity, which means that actually, despite the vanishing of the leading coefficient, solutions extend holomorphically to the point. Then there is a slightly more involved singularities, which, well, here the terminology is awful because the usual word is regular, which is a regular singularity. It's an oxymoron, so it offends the feeling of any normal person. So I would prefer to call them moderate or tame. And the definition is that all solutions of this singularity grow no faster than polynomially when you approach the singular point. Here one have to be a little bit more careful. So it would be just like a definition of a pole of a meromorphic function. So one has to be slightly careful because of the multivaluedness, because you need to constrain solutions to some slit or simply connected domains. So when looking at the growth of solutions, you need to approach the singular points along a relatively straight line and not along a spiral. And finally, there are wild or irregular singularities, which are exhibiting faster than polynomial growth of solutions. All three types naturally happen. Now, it turns out that the classification, unlike the case, the classification of singularities by their growth type is very explicit and constructive. So one may look at the relative orders of poles of the coefficients at each singular point, and there is a certain condition, arithmetic condition, just integer condition, which guarantees that solutions of the differential equation will grow at most polynomially, would have tame growth. And therefore, we have an explicit test showing that the equation has all singularities tame. So such differential equations are called Fuchsian. I didn't want to stop by and explain in detail how this condition looks like. I just give a brief indication. So if you are working near a singularity at the origin, so how do you formulate the Fuchs condition? So what you do is the freedom of the choice of the derivation on the ring of polynomials. So instead of the standard derivation delta, which is d over dt, you introduce the Euler derivation, which is t d over dt. And this Euler derivation you can use to re-expand your polynomial, your differential polynomial, and then get rid of the denominator so that the result will be in the ring in two non-commuting variables, but now there are not t and delta, there are t and epsilon. And the Fuchs condition, the easiest way to memorize the Fuchs condition is the following. Do the re-expansion, cancel everything, cancel all denominators, cancel all common factors, and then you get an equation. If the leading coefficient is non-vanishing, then the equation is Fuchsian at the origin. If you need to make this test at another point, you just replace, make a translation, and the same test literally shows you, gives you the Fuchsianity condition at the point infinity. Another important remark is the difference between scalar equations of high order and systems of first order differential equations, which have the following structure. So you have n differential, n independent variables, n dependent variables. The time is still complex one-dimensional, and you have a matrix of the coefficients. Here, the Fuchsian condition is usually formulated that the system has a first order pole at a given point. So the first order is good, higher order is bad. But unlike differential equations, the Fuchsian condition for systems is sufficient but not necessary. You can easily have a system of equations whose solutions grow moderately at the singular point, but which has an higher order. Just take any meromorphic matrix function and compute its logarithmic derivative. Chances are that you will get, if your matrix function was chosen more or less at random, then chances are that you will get a higher order pole. Now, having introduced the players, we will formulate our goal. So what we want to study. What shall we do with a drunken sailor, as the Scottish song says? So we will be mostly interested in studying the oscillation of solutions to differential equations, which is quantified in terms of the number of isolated zeros of their non-trivial solutions. So we pick an equation, take a non-trivial solution, and try to find how many zeros it is. So the answer, of course, depends on the equation, and you can look at the mathematical pendulum equation on the real axis, which is the second derivative plus my. Second derivative of y is 0. And m, the coefficient, the only non-trivial coefficient of this equation, is the square of the frequency. So when m grows to infinity, you get sine and cosine with more higher and higher frequency. And so no matter how and where you count zeros, you get the result that will grow to infinity. But there are actually other difficulties to be addressed. First, we need to decide which solution we choose, because there is a whole dimensional space of them. Well, here the answer is, of course, we try to find a uniform bound. The next question is how you count rules of multivariate functions. Here the answer is also more or less obvious. You just split your complex domain with several deleted singular points into simply connected domains and choose branches of the multivariate solution in those domains. Actually, the choice of another branch is just the choice of another solution of the same equation. So those two problems will be solved at once if we do like this. Second and third question, in what terms you expect the answer? and when you can expect the answer. So it is clear that for non-Fuchsian equations, you should not even expect anything reasonable. And the explanation is classical. So if you recall the classical Picard theorem, then it says that near an essential singularity, which is not a pole, any function takes infinitely many times all complex values. So even without any differential equation to work with, if you have a essential singularity, the answer will be typically infinite number of zeros accumulating to this point, nothing to to deal with. But in general, as the example here suggests, we should expect the answer depending on the differential operator and given in terms of the relative magnitude of non-leading coefficients. If the differential operator has large coefficients, then it should have more zeros, well, probably even infinity. But because we are in the projective situation, so we need to measure the magnitude of the coefficients relative to the leading coefficient. So you should bear this in mind. So we start with the question, what we can do without singularities. So without singularities, we can divide out by the leading coefficient and get a monic operator whose leading coefficient is just 1. And then we have other coefficients which will be holomorphic in the domain where we consider this equation. Assuming that this domain contains no singularities, we see that the coefficients have no poles there. Therefore, they are explicitly bounded. And we have the following problem, which is formulated as follows. What you know about your differential equations? First, the order. Second, you know the size of the domain in which you consider the problem. So if you are on the real axis, you fix a finite interval. Infinite intervals may be problematic since, for instance, even if the coefficients are constants, the equation may have infinitely many zeros on unbounded intervals. And then we have the upper bound for the non-leading coefficients. So we take all coefficients, majorize them in U, and take the maximal value. The theorem, which is which goes back to de Laval-Poussin in the real context and was generalized by a number of steps, including myself, tells that these data, the size, the order, and the magnitude are enough to place a fairly explicit, absolutely explicit upper bound on the number of isolated solutions. I don't write these upper bounds. Well, it's, you don't. When you need it, you know when to find the formula. What is important is that you can write an explicit expression measuring the number of zeros. Next question is, what about the Fuchsian equations? So as I told you, the Fuchsian equation assume that it has a Fuchsian singularity at the origin. And so in order to study it, we replace the derivation by the Euler derivation. And by Fuchs condition, we can assume that the coefficients can be divided out by the common factor so that the leading coefficient with respect to this Euler derivation is 1. So assuming that here is 1 is exactly assuming that the origin is a Fuchsian singularity, and assuming that the other coefficients are holomorphic in our domain is equivalent to assuming that there are no more other singularities. Now we can sort of mimic the same strategy. And what we can prove is the following statement. So we have the same collection of data. So we need the order of the equation, the size of the domain, and the relative magnitude of non-leading coefficients. So all of those three ingredients are important. And you can write down the upper bounds for the number of equations, but assuming an extra assumption. This extra assumption is the following. You freeze the coefficients of this equation at the origin. So you take constants beta that are values of bj at the origin. You write the corresponding characteristic polynomial, and you assume that all its roots are real. Why you need this assumption? Because without this assumption, you can really easily write down a very decent equation whose solution is y is t to the power I plus t to the power minus I, where I is the imaginary unit, which is 2 times cosine logarithm t. And of course, this function has an infinite number of even real zeros accumulating to the origin, although the coefficients of the corresponding equation provide no reasons to suspect such ill behavior. So this extra spectral condition is really necessary. Now, how we can combine, in a sense, those two results? It seems that we solved the problem by part. We know how to count zeros in the domains free from singularities. We know how to count zeros in the neighborhood of an isolated singularity, provided that is Fuchsian, and this is the obvious condition which we cannot drop, and provided that the roots are real. So what you do is you just cut your complex plane into puncture disks around singularities, and the complement which you split into simply connected domains, and use those two results separately in each domain, and then you just add together the corresponding upper bounds. So this would give you the solution for all Fuchsian equations. So in which terms it will be given. Of course, you still have the degree of the differential equation. You have the number of singularities. Well, it depends on the degree of the polynomials. The more singularities you have, the more times you need to use theorem D. Now, it depends also on the configuration of singular locus. And I'll try to explain why later. And then we still need some numeric measure of the magnitude of the non-leading coefficients, which will be uniform over all singular points. So we need to, well, of course, we can use the maximal, the bound for each singular point, but we wouldn't like the formula which depends on 25 parameters each for each singular point. We want to have something simple and useful. So what we do is we introduce the following notion. So we reduce, as I said, the differential operator to the form where all coefficients are polynomials, and of course mutually prime. And this condition defines us coefficients up to a constant multiple. So now we have a genuine projective space. And in this genuine projective space, we can introduce the relative measure of the non-leading coefficients as follows. We take some norm on the space of polynomials of the given degree. And this norm is just taken as L1 norm of a polynomial, the sum of absolute values of its coefficients. And then we take the maximum of all ratios of such norms. It is clear that this is indeed a numeric measure of magnitude of non-leading coefficients. It is not exactly the measure that we used in theorems A and B, but it is actually very close. And for one simple reason, if you have the leading coefficient A0 of norm 1, then it can be small only near the singular points. Outside of the union of singular points, it is explicitly bounded by some inequality. This classic inequality is called the Carta Inequality. I don't write it, but it is this boundedness from below that allows us to use theorems A and B the way it was formulated. And now just an example of what is a slope. We can consider the case of equation with the constant coefficients. Then all those coefficients, their norms are just the absolute values of the coefficients themselves. And the slope is indeed the most intuitively understood relative magnitude. And then we can indeed prove the following theorem. It is also formulated without writing any explicit formulas, but it gives you the answer in terms of the slope of a differential operator and the configuration of the singular locus. Well, it's configuration is a geometric notion, so you need to explain which configurations are good, which are bad, and how they contribute to the growth of the bound or to its moderate nature. The contribution occurs, well, the bound becomes bad and diverges when Fuchsian singularities merge together. Okay. Now, maybe I will just skip this slide. I will explain, well, just say a few words of how the slope should be understood by the people who worked all their life with differential equations. What means uniform smallness of the leading coefficients? So you just introduce an imagined parameter epsilon, small parameter epsilon, and you assume that your parameter occurs before the highest derivative. And and the other coefficients say depend analytically on this parameter while remaining polynomial in T. So how do you call, then you get a one parametric family. How do you call such family if epsilon goes to 0? The answer is uniformly known. It's clear. It's called a singular perturbation, singularly perturbed family. And people with the minimal experience, I hope that Robert and Freddy are watching this record. But actually, it's a common point that singular perturbations are one of the biggest pains in the back. So solutions may explode to infinity. The equation has several time scales, namely it has slow time, epsilon t, and fast time, and you need somehow to marry the fast and slow dynamics of solutions of the differential equations. Next, most formal methods of expanding solution into a series do diverge. And this divergence is not an accidental stuff. It reflects some very deep properties. Well, people who are closer to mathematical physics, of course, recognize that such singular perturbations give rise to fast oscillations and short phase integrals. So the danger of having a leading coefficient becoming uniformly small is really very serious. And somehow, if we have a problem in which there is some natural parameter which occurs before the leading coefficient, then you should be very much aware of what's going on. Okay, but it looks like we took care and introduced the notion of the slope that prevents us from falling into this trap of singular perturbation. If the slope is bounded, then the relative magnitude, uniform magnitude of the coefficients is bounded. But once you think a couple of minutes about the definition, you see that it kind of is a, well, it's self-illusion. Why? Just consider an equation with constant coefficients. So Cj are constants. And then make a rescaling of time. So you introduce a different time, mu being the parameter, and make the variable, the change of the independent variable, and re-expand this operator in terms of the new transform time. So what you see is that the coefficients of this parameter mu appear in a non-trivial way. Well, of course, you need to do this computation and then cancel everything, non-trivial way before the coefficients. And note that I didn't say anything about the mu. It could be very small or it could be very large. So playing with mu, I can take a differential operator with constant coefficients and make its slope large or small, just ad libitum, as I may wish. Which means that actually for such an operator, the slope is kind of meaningless. Why? Because such change of variables does not change the number of roots. I just rescale the time variable, but if I want, I recall that I want to count roots globally, so not in some domain which will become smaller or larger when I slit my plane, split it into domains. I am looking for a global bound. Well, there is even worse problem. Suppose that you make a conformal change of the variable. So I recall that we live on the projective plane, and I have the whole Möbius group of transformations at my disposition. And these Möbius transformations act on my differential operators in the most terrible way. So you start with polynomial coefficients. Because the transformation is only rational, after you change the variable, you get rational coefficients. Then you have to get rid of all the denominators and cancel all of them and cancel all possible common factors. And then you get some new differential operator with polynomial coefficients, which has another slope. Well, this operator is denoted by mu, pullback of L by the Möbius transformation mu. So the result will, of course, depend on the chosen transformation. Moreover, if you try to figure out the result, it will be hopeless mess. You cannot expect that you can be able to make all those computations by hand and arrive at any answer that is reasonable. But here comes the surprise. Here comes the surprise, and this surprise says as follows. Suppose that my operator was Fuchsian, meaning that it has only Fuchsian singularities throughout the projective plane, and that it has some slope sigma 0 in the initial affine chart. Then, regardless of the fact that the Möbius group is not compact, and I can do a lot with the coefficients by transforming this equation, the slope of what I get, the slope of the pullback, will be bounded between two constants, depending only on the initial slope. So I won't claim that the slope will be preserved by the Möbius transformation. I only claim that if it was very small, you cannot make it very large. Or vice versa, if it was very large, you cannot make it very small. So you have kind of pseudo-invariance. This is a non-rigid invariance. And this is the surprising fact. To illustrate this surprising fact, here are two examples. First is the Euler equation. So what happens if I take the Euler equation with constant coefficients? And of course, because it is Euler, I expand it is in the powers of the Euler derivation. So what happens if I do just a usual rescale, change of scale? This operator is invariant by such rescale. T gets multiplied by mu, d over dt gets divided by mu, and altogether epsilon stays the same. So the usual rescale, but I stress that a rescale homothety centered at the origin does not affect the Euler equation. So if my group is limited to just homotheties centered at the origin, then the slope is an invariant for Euler equation. But then what happened with the equation with constant coefficient? So we have a polynomial in delta, the usual derivation. So how did it happen that by rescaling, by homotheties, I can change its slope? That is very simple. The point at infinity for this equation is non-Fuchsian. Solutions of this equation with complex coefficient are growing, are exponentials, and they grow faster than polynomials at infinity. So this example does not contradict the theorem of quasi-invariance of the slope. And this Euler expansion gives some flavor, some feeling of why it holds. Now, I am approaching the second part, and in this second part, I will try to formulate the problem in a parametric way. So I already discussed how you can introduce parameters to make one-parametric families and singular perturbations. Now I will explain how you can have natural parametric families of Fuchsian equations. So the typical situation is as follows. They come from Fuchsian matrix equations. So suppose that you have the projective space highly dimensional, multidimensional. And suppose that on this projective space, you have a rational matrix one form. So this is a matrix whose entries are one forms with rational coefficients in several independent variables. So what is important here that the dimension of the independent variable just grew up from one, what was the typical situation up to now, to several variables. Now, we consider the following Fuchsian system, which means that we look for matrix valued functions whose exterior derivative is omega x. So you should instantly recall the equations of the form dx is equal to a of t dt times x. So if the variable were one-dimensional, then we would have one-dimensional matrix form. All forms are proportional to dt. There are no other independent variables. And here, your Fuchsian system would become a system of first-order homogeneous equations. How you can bring this one Fuchsian multidimensional system to a family of parametric family of Fuchsian equations? The answer is very simple. You take all projective lines inside CPM. So they form an algebraic variety. It will be a Grassmann variety. And for each such line, now I plotted two-dimensional because it is a complex one-dimensional, we can restrict our system. The system had poles. The form omega is rational, so it has poles, singularities, and so those poles, which usually form a hypersurface of codimension 1, will cross typically your randomly picked projective line by isolated points. And then you write just down you constrain your system on this one-dimensional line. So you have a system of one-dimensional equations, and everybody knows that such system can be reduced to a nth order differential equation. This reduction is also kind of tricky because you cannot realistically estimate the slope of the corresponding equation. This equation will be homogeneous, but its slope could be arbitrarily large. Why? Because the standard algorithm of derivation says you take vector x and then start computing its derivatives by virtue of the system x dot, x2 dots, x3 dots, x4 dots. Because you are in a finite dimensional space, at a certain moment, those derivatives will become linear dependent over the field of irrational fractions. And any such dependence is basically a linear ordinary differential equation. But think about even the following situation, which is simple. You pick vectors from some n-dimensional space and look for the first time they become linear dependent. So even assuming that your vectors are all of unit length, so they do not grow, you can easily have a situation when the first two vectors are linear independent, but form a very small angle between them. And the third vector happens to be in the same two plane, but almost normal to those two almost collinear vectors. Then, of course, you can write down the linear combination, but it would have enormous coefficients. You would have to divide by some determinant, which by construction is not zero, but nothing on Earth prevents it from becoming very, very small. So in theory, you can reduce a system to an equation. In practice, you absolutely lose control of the slope in this process. On the other hand, what we have a different nice feature is that the corresponding family will be isomonodromic. What it means that if you have two close lines, then they would close the singular locus by close points. And so you can trace the loops around those singularities. And those loops will have the same monodromy operators because the system satisfies the flatness condition. It's Frobenius condition. Okay. Here is the result that is one of the keystones of our proof of solution of the infinitesimal Hilbert problem, meaning the following. Suppose that we have a family that we started from a family like this, and we ended up with a family of Fuchsian equations. This condition can be guaranteed automatically if we know for some reasons that solutions are not growing near the singular locus. Then it turns out that the slope, which is a priori only a rational function. Rational means that it may have poles. Well, you remember how we introduced it. It's the fraction of two norms. So it may well have poles when the leading coefficient vanishes. But it turns out that this slope is bounded on any algebraic subset. And moreover, this bound is explicit. If for some reasons our form, which depended on several independent variables, was defined over Q, meaning that it had only rational or integer coefficients, then knowing those coefficients, we can place an explicit upper bound on the slope. So the fact is that if your family of equations is globally Fuchsian, then the slope cannot grow. It cannot grow to infinity. So this is based on the following theorem, which is valid for one-dimensional systems, which says that the slope is locally bounded. Locally means near every point. And this explicit formula is more or less standard corollary from the effective algebraic geometry. So if you have a semi-algebraic set which is defined by polynomials with integer coefficients, and those integers are not very large, the point may well be unbounded. Think about half plane, x greater than 0, x1 greater than 0. But if this plane, this set is bounded, then you can place an explicit bound on its size. So it's kind of a common issue in some things. Now, how this helps to fight the collision of singular points. As I said, if you have two colliding singular points, then you have a problem. Indeed, look at the Fuchsian equation with the singularity at the origin and assume that it has another singularity outside of the disk t less than r, which converges within our family to the origin. This would mean that the coefficients are unbounded, because they would eventually have poles when the extra singularity, the additional singularity, crosses the boundary of the disk where you study. And this would ruin your theorem B, which gives you an explicit upper bound. Why this situation is now not a danger for us? For one simple reason. We proved that the slope is conformally invariant, which means that without changing it too much, we can always take any two singular points to the distance at least 1 apart. So this is very unusual. You are familiar with the situation when if you have a collision of singularities, collision of singular points, then you would expect some denominators vanish, some derivatives vanish, something would go wrong. Not in the case of Fuchsian families. In the Fuchsian world, you can carry any 2 points to a distance apart, and even more, you can carry any 3 points to, say, 3 vertices of a triangle of size 1. So your construction instantly becomes stable by desingularization, by the blow-up. So the blow, after all the preliminary work I explained, we can use blow up, and this never results in anything bad. So now, finally, how this is related to the Hilbert 16th problem and periods of Abelian differential. So this is more a thing that I explained several times. So I will just briefly recall what's going on. You consider all Hamiltonians of degree d+1. And you consider all their level curves, zero level curves. Zero level curve means that your Hamiltonians make sense only up to a constant multiple, and therefore they form a projective space. So I call the set of all Hamiltonians this projective space, which I explained here. Now, where do I get my Parthian 1 form? Very easily. I take all monomial 1 forms of degree, well, it should be I plus j, ij less or equal to d. And I notice that the genus of a typical zero curve, h is equal to 0, is exactly equal to the number of those forms, which means that if you take their monomial preimages, they will become cohomologically independent on a typical curve, which means that if I form the corresponding period matrix, this is a matrix function whose entries are integrals of the monomial preimages of those forms, over all non-trivial cycles on the level curve. This construction is well, it's not completely innocent, because we can have all kinds of problems. First, accidentally, we may have the forms cohomologically dependent. Second, among the level curves, we may have very singular level curves whose, and if you have a singular curve, it's not clear how you define its cohomology. Its homology. So we have to delete out some exceptionally bad level curves. But what is important for me is that the remaining set will be still the open dense projective open dense set of the projective space. So my matrix form is defined there. And finally, I just take its logarithmic derivative. So because x and dx have the same monodromy, this follows from Picard-Lefschetz formulas, this logarithmic derivative is single valued. Because integrals of monomial forms grow at most polynomially, the singularities of the form omega on the set that I did not even bother to explicitly describe, well, I described it, but I didn't write formulas, will be at most tame. And so what we see is, okay, will be a one form. So it remains just to ask one question: why it is defined over Q? And the answer is, it is because there are no more parameters left. So all coefficients of the Hamiltonian H, we declared independent variables. So the H as a function of those independent variables has coefficients only 0 and 1. So there are integers. All monomial primitives of those forms are the same, and they are also defined over 0 and 1. And finally, to explain the derivation, we need just to recall that it can be done explicitly. Computation of the derivation can be done explicitly using the Gelfand-Leray division algorithm. So we start with some data, initial data that have only zeros and ones. And then we run some irrational construction. Rational construction involving known number of steps, so it's a known complexity, which means that no matter what's going on, we cannot produce too large systems, too large number of coefficients. So they will be first irrational, and second, we get automatically a bound for the degree of the system. So as a result, we have this theorem on the number of isolated periods of, on the number of isolated zeros of abelian periods. And I just glossed over one slide, which I didn't have time to explain why my spectral condition holds. This is a non-trivial assumption, because what I would have to do is I would have to constrain my Fuchsian system on all projective lines in the projective space, look at all singular points, look at all characteristic polynomials, and see that all the roots of those characteristic polynomials are only real. I don't need to do this. It turns out that there is a wonderful theorem due to Kashivara, which says that I can check only the generic situation. I need only to check singularities, which occur when my projective line crosses the polar divisor of omega at a smooth point. And a smooth point of the divisor is the point where exactly two more singularities collide. And this is a well-known Picard-Lefschetz situation. You know what happens with a function when its two critical Morse points collide generically. Behavior of the only non-trivial behavior of cycles is described by a matrix, which is a Jordan matrix with eigenvalues only 1. This is enough by Kashivara theorem to guarantee that actually for all eigenvalues of all characteristic polynomials will be rational numbers and therefore real. Well, unfortunately, I have no time to provide here details, so thank you for your attention.
Okay, thank you, Sergey. Questions?
Sergey, so let's consider the most simple case, let's say, and say that we are interested in the multiplicity of zeros. Pavon has an old article giving a polynomial.
Yes,
I wanted to know, in the case of multiplicity, if you apply your method, is this upper bound get improved or still?
Of course. Multiplicity is a much easier thing because you don't have to deal with differential equations. You have to deal only with orders of their coefficients, which are at the end of the story just the orders of zero of certain Wronskians. And this you can do because those Wronskians are rational or polynomial numbers, and this Pablo wrote did 30 plus years ago, and his bounds are polynomial. The bounds which I get are, well, so in somehow the whole point was to avoid all explicit calculations just by sweeping the corresponding results, the corresponding theoretical possibility under the carpet. So if you wish, the double exponential bound comes exactly from the theorem in effective algebraic geometry, which I mentioned. And people in this area know quite fairly that the double exponential bound is something that is apparently inherent for explicit estimates in this. So it's a double exponential curse of dimension. So in linear programming, the dimension affects exponentially the complexity of computation, but in the real algebraic geometry, when you need to work with ideals and not geometric shapes, your bounds become one double exponential. And of course, if somebody would be able to do those computations in a mysterious way explicitly, which I don't believe is possible, then one could perhaps hope for something more realistic. But as long as you need only philosophical result, then that's the best you can do. Actually, it is indeed kind of philosophical question, actually now close to the mathematical logic. So we know that there is an algebraic geometry, the area where you can some things compute precisely, and if not compute precisely, then at least place easy upper bounds, like Bézout theorem majorizes the number of isolated roots of a system of algebraic equations. Once you go across the boundary of algebraic world, and if you allow transcendental functions, then your world is ruined almost immediately. If you are you want to remain in the real situation, then you still can allow exponentials and logarithms. And this is the so-called theory or minimality theory. So this structure involving exponentials and algebraic numbers is one of the precious few known minimal structures. But once you are over the complex numbers, and we are over the complex numbers because complexification is the key tool in all this story, then it looks like whenever you cross the frontier of algebraicity, you fall into the wild jungle of functions with and objects with infinite complexity, infinite number of zeros, infinite number of connected components, and so on. So our result shows that there is still a thin layer or boundary layer, which we describe as Q functions. The functions described by Pfaffian systems, integrable Pfaffian systems, defined over U. And those Pfaffian systems still provide us with the with non-algebraic functions, transcendental functions, obviously transcendental functions, which still behave very, very remotely like algebraic, meaning that they define geometric objects not very well. So how thick is really this layer? And if there is any possibility of moving farther across this class of Q functions, we do not know. So, well, Guy is working now on some multidimensional generalizations of this, but I want, it's definitely not 2 minutes remark.
Okay, more questions?
I have a question in the last theorem. This 61 has some special meaning, or is just...
No. This 61 is just the result of computation. So sometimes we need certain dimensions should be squared because we count the number of monomials in two variables constrained by dimensions. Sometimes we have them. We had to write down explicit bounds which involve third powers. So it is, we never try to save on these degrees. So nothing transcendental, nothing mythical, nothing sacred about this number. It's just what we got being completely exhausted. The simplest thing to write down that should certainly work.
I see. Thank you.
More question?
Hi. In the bound of the In the bound of this infinitesimal Hilbert 60th problem, it is necessary to have the degree of the deformation smaller than the degree of the Hamiltonian, or you also have a bound for when the degree is greater?
So this is okay. So maybe this is worth a minute digression. So, of course, we can allow arbitrary combination of degree of the polynomial and the form. The choice was made simply because when we go back to the initial Hilbert's problem, then we want the perturbation to be of the same degree as the unperturbed Hamiltonian system. And so it was natural there. There is a good question. If we make the two parameters independent, one, the degree of the Hamiltonian, and the other is the degree of the form, can one do better? Yes. Yes, one can do infinitely better with respect to the degree of the form. You can produce a bound that will be not just double exponential, not polynomial, but linear in the degree of the form. It's the coefficients of this linear dependence, the free term, well, basically the free term, the linear term is very explicit and easy, but the free term will be double exponential and maybe even more horrible than we wrote here, but the dependence on the degree of the form is will be linear and I would say quite natural. This is a work which was done by a high school student who came for a summer practice to the Weizmann Institute and got Galbin Yemini as an advisor during this practice. Well, the student is now a mature mathematician, but the reason is very easy. If you look at the period, then it depends on the form in a linear way. And whatever is linear is controlled by the dimension. And the dimensions are always easy to estimate and control. It is the dependence on the Hamiltonian, which is most highly non-trivial. It has poles, it has singularities, it has all kinds of degeneracies, and all of them contribute to this horrible bound. But whatever is linear can be done by linear methods. Well, in fact, if you think it is spiritually very close to what Pavel did in his paper that was already mentioned. So the formal construction was different, but the grand idea is essentially the same.
Thank you.
More question? My question. Okay. One question. When you were talking about the Mobius transformation, one question that arises for me is when, if we consider one special case of the hypergeometric differential equations, for some choices, the solutions are modular, for some choices are not. And then I'm wondering if there is any study in your setting about them, or?
No, I never thought about any practical applications of all this theory. So what is clear is that first, hypergeometric equations are indeed Fuchsian. And you know when they have the real eigenvalues, it's also it's a well-developed theory. Now, they have auxiliary parameters which reflect the magnitude of the non-principal coefficients. In theory, you can, well, You can actually, with them, you can do more easy. You can place their singularities at the standard places, 0, 1, and infinity. And then so you just freeze it. You are spared the most dangerous phenomenon of collision of singularities. Whether the answer given in terms of given by theorems A and B that I mentioned at the beginning of the talk will be interesting or not, I have no idea. I am almost sure that people, hypergeometric equations were so much experimented with, so people know about the distribution of their zeros much more than I could say just roughly comparing their oscillation with the oscillation of, say, trigonometric functions. So I wouldn't expect anything really interesting or novel here. Well, one reason, as I said, is because the collision of singularities is not a problem in this hypergeometric case.
Okay, thanks. So let's thanks again, Sergey. Thank you, Sergey.
Okay, thank you for your attention. Thank you for your questions. So they were all to the point. Au point.
Yeah, when you started, it was day. I think now it is night. Yeah.
Adios, a luego.
Yeah. Bye bye.